Cape Talk, the world of science with Dr. Chris Smith, the naked scientist.
Good morning, Chris. How are you this morning?
I'm very well, thank you. And you?
I'm well, very well. I'm enjoying a little bit of sunshine peeking through without much cloud in the sky for a change.
Well, we've been, as you've probably seen, enjoying, if you can put it that way, a dramatic heat wave because Europe has been roasting. We've had temperatures, not in the UK, thankfully, but in France, 46 degrees Celsius, a world record for France ever. And then people turn around and say that there's no such thing as global warming. I mean, this is ridiculous. We've had 20 years of successive record-breaking temperatures in all parts of the world.
Correct. You're absolutely right. I don't know if you saw that image of the weather map that made it look like the Scream, Edvard Munch's The Scream, over where it looked like faces. France was a face that was melting. And anyway, it went viral.
Yeah. I mean, it's same story here, though. I mean, we've had unseasonably hot weather, and especially the weekend before last. Because last weekend it was really cool, in inverted commas, because do you remember we were launching this balloon into space? And I was slightly nervous because when you're putting a helium balloon up into space, the rate at which it climbs and the height to which it can ascend is going to be proportional to how warm the air is. So if it's really, really hot and sunny, the balloon is going to have less lift than if the air is thicker and heavier. But luckily, we still made it work. And we got our balloon to the edge of space, 33 kilometres up. We've got the most staggering pictures. But we also did succeed in our remit to record the screams of listeners from space to see what they sound like, because we were testing the theory, in space no one can hear you scream. And we invited people who listen to The Naked Scientist all around the world to send in screams, which lots of people did, and we selected the best one. The best one was definitely Noha from Cape Town. because, but I've got the recording. Would you like to hear what this actually sounded like? So what we did, we recorded every 5 minutes. So we played a loop with a succession of these screams in there. And every 5 minutes we also logged the altitude, the pressure, the temperature, etc. And we did that all the way up into space. So the first one I'll play you is what the rig recorded at ground level. So this is what basically it sounds like. So I'll play that for you now. Here we go.
Children, come and clean your room! Woo-hoo! Hungos! Ollie, dolly, treat!
So that's as the balloon is just taking off. I know.
They're so creative. I love the harmonies. Okay, go ahead.
And then when we get to 33 kilometres, what we were anticipating is, because the air is becoming thinner with lower pressure the higher you go, and sound is a compression wave where effectively you push against molecules of air, those air molecules buff it against other air molecules, and they reverberate across the airspace until those molecules then bash into your eardrum and put a pressure on it to make it move. Or in our case, we had a microphone sitting there, and they bash into the microphone and they make the microphone move. So the more air molecules there are to make the microphone move, the louder the sound you hear. And conversely, the fewer air molecules there are moving, the less the pressure on the microphone, the quieter it's going to sound. So our prediction was that the higher we got, the quieter it will get. And indeed, this is at 33 kilometres. You're going to have to listen really carefully, everybody. Do not adjust your sets. Now, the point is that was played at identical volume. The same energy was going into the speaker, but because there were very few air molecules there, the pressure was actually less than 1% of what you get at ground level at 33 kilometres. Therefore, you're moving far fewer air molecules, and because you're moving far fewer air molecules, there are fewer to bash into the microphone. So we record a quieter sound, even though it was played from the speaker at the same volume. Ergo, if we'd carried on up into the sky to what we judged to be the real margin with space at about 100 kilometres, there would be so few molecules there that there would be almost no pressure being applied to the microphone. So therefore we can say case closed. You wouldn't be being heard screaming in space.
Love that experiment. Thanks for that. Keith wants to know, is it true that we don't need our appendix, and what is its purpose in our body?
Good morning, Keith. Well, the answer is that the appendix is actually properly called in medical terms the vermiform appendix, vermis meaning worm. and it does look like a worm. It's roughly the size of your small finger, and it dangles off of the first part of your large intestine, the cecum. And if you take out the appendix and look at it, you see that there are lots of aggregations of what we call lymphoid tissue in there. Lymphoid tissue is a collection of white blood cells. So we think the appendix is an important site where the immune system is being introduced to various things that live in you and that you take into your body in food, and it's therefore being educated about how to respond to various potential infections, the friendly bacteria and other friendly things and unfriendly things in what we eat. You can do without it because most people who develop appendicitis, which is inflammation of the appendix, are fixed by a surgeon going in and tying off the base of the appendix to seal the bowel and taking away the damaged appendix. Most people, by the time they have it removed, probably have had it do all of the important immune jobs that it's going to be needed to do. Therefore, they don't suffer any kind of ill effect if they have it removed. So that's probably the reason why we've decided we can live without it. But you see, evolution is a clever thing, and it normally gets rid of things that we don't really need. So therefore, if it were that inconsequential, it would have eventually disappeared all of its own accord. So the fact that it is there argues it almost certainly has some role to play. And in some animals, it does a very important job. In animals like rabbits and things that eat their own feces because they rely on various enzymes carried by bowel bacteria to break down things in the food that their own bodies can't. The appendix plays an important role in that. But in humans, luckily, we don't do that. We're not coprophagic, but we do have an important immune function that comes from our appendix. But by the time we usually get rid of it, it's probably already done its job.
Got it. We've got a voice note for you here.
Good morning, Chris. Question inspired by my daughter. We're watching a movie, and in one of the scenes, a burning couch, is pushed out into space, and it burns. And I explained to her, but that doesn't make sense because there's no oxygen in space, and so the couch wouldn't burn. So, that's a movie error, a movie myth. And then she asked me an interesting question. She said, but in that case, since the sun is just a floating object in space, why does the sun burn if there's no oxygen in space? And I thought that was quite an inspired question. I'd love to hear your answer. Thank you.
It is an inspired question. And the answer, first of all, let's look at the sofa question, because that's quite right to condemn that. Because if the sofa is burning in air, it is using oxygen as the oxidant from the air to keep the fire going. Because a fire consists of three things: a fuel, an oxidizing agent, which when we light a fire on Earth, that's oxygen, and heat, because you've got to turn the fuel into a vapour, which is a gas form of the fuel, and mix it with the oxygen for the chemical reaction to be triggered by heat. So if you just pushed a burning sofa out into space, several things are wrong with that argument. One is, yes, space is very rarefied. There's maybe 1 atom per cubic metre or so in deep space, so there's certainly no oxygen there. So unless the sofa material is making some source of oxygen or some other oxidising agent that will keep the fire going, that's not going to work. But more importantly, let's assume that this is in orbit around the Earth. It's going to be in free fall. And if you're in free fall around the Earth, there is actually no up or down. There's not the same density gradient that there is on Earth. If I light a candle on Earth, what's happening is that the hot gases rising above the candle are less dense than the air around the candle, so the hot gases rise upwards and get out of the way, and fresh oxygen-rich air can come in from the bottom, and that's what keeps the candle going. Whereas, if you did that in space, because there isn't an up and down like that, then all that would happen is the waste products would just accumulate around the candle and choke it off because the fresh oxygen wouldn't be able to get in. So the sofa wouldn't burn like that. In terms of the sun is not a burning like a log fire or a barbecue. The sun is a giant fusion reactor. It's a nuclear reaction where it's 1,000,000 times bigger than the Earth, and because of its enormous mass, there's very high pressure at the centre of the sun, which is crushing under gravity atoms of hydrogen together. And when 4 atoms of hydrogen are squeezed together very hard, they fuse to make 1 atom of helium. And that helium weighs, in inverted commas, slightly less than all of the sum of the 4 hydrogens added together. And that difference in weight, amongst a couple of other things, corresponds to heat. And so the sun actually emits the energy as light waves, photons of infrared, which is what then we see, and it keeps us warm. So the sun is a fire. It's hot. It's at the surface about 6,000 degrees Kelvin. In the middle, 15 to millions more degrees. But it's not a fire, it is a fusion reactor, and it's hot because that fusion reaction is chucking out heat. And every second the sun loses about 8 million tonnes in mass, corresponding to the heat and light that it's chucking out into space.
Wow, very interesting stuff. Now, Dan wants to know, has a study ever been done to quantify the amount of water lost to nature's reticulation process, which is contained in manufactured products globally, such as tinned goods, bottled drinks, paints, and the like?
I'm sure they have. People have done very careful studies of what we dub embodied water, because we're very worried about water consumption, not just in South Africa, and obviously it's a subject close to Cape Town's heart, but all over the world, because people are predicting in the future, as world populations rise, as climate change means that the area of livable land will change, and our current estimates are that the amount of livable land will drop. In other words, areas are going to get drier, some areas are going to get a lot wetter, and the result is that the areas that are just right, sort of Goldilocks places to live, will shrink. And that means that the water availability in those places will come under higher stress because there's going to be more people living in a more crowded situation. So people are very interested in how we conserve water and how we use water more diligently and more judiciously when we're making things. And so, yes, there are lots of calculations to work out the embodied water in things. Like one estimate I saw when someone said, when you build a house, the embodied water in building a house for all the materials and the furnishings and so on is like taking that house and filling it up with water several times over. That's the amount of water that goes into the process of just making that house. Making a car, similar. The steel making process to make a car uses huge amounts of water. So yes, those calculations have been done. There will also be consideration about whether or not you export and import things. People are talking about, for example, I could grow tomatoes in this country, but tomatoes use a lot of water. So instead, if I buy my tomatoes from another country which has got lots and lots of water and pay the shipping cost to bring them in, actually the water cost is offsets totally the transport cost, and it's still better for the environment that way. So yes, people are looking at this increasingly. Do I have access to the data for those figures? I don't know exactly what reference to give you, but certainly if you look up embodied water in manufacturing, you can find that. And it's a very good point you've made.
Fantastic. This is a creepy one. Eek. Ouch. How does the body know how to regrow fingertips? Mine came back okay after a nasty kitchen accident. Eek.
Ooh, it depends what you chop off. If you chop off just superficial tissue and you don't damage the underlying stem cell baseline where you regenerate your cells from, then you can regenerate the tissue above that layer of stem cells, no problem. And we do this all the time. Whenever you sort of scoot your foot along the floor, you're rubbing off thousands of cells. Most of them are just dead, flattened, dried out cells that are there to provide a cushion. Occasionally, if you penetrate into the soft tissue, it's going to hurt, but you're not actually going to damage the stem cells that are there to repopulate that thick layer of cells. But once you go through that crucial layer into the deeper tissues, that's where the scaffolding is that tells the cells as they grow how to make the end of your finger. And there's more complex arrangements of cells there. And if you disrupt that, then A, you're probably going to get a scar at best, and B, it may not grow back properly. So traumatic amputation, in humans at least, you can't regrow it. There are animals, though, that can. And there are animals, for instance, like a salamander and even, fish and things. If you take off part of their body, or you damage quite catastrophically an organ, you can chop out part of the heart of a fish, for example, and it can regrow it. And scientists are really interested in this because this means these animals and nature itself can do what we would really like to be able to do in a person who's, say, got a disease or lost a bit of their body or damaged something, regrow a new one. How do they do it? Well, they seem to have much better stem cells which are capable of regressing quite quickly back to a more primitive, unspecialized state and then regrowing from scratch the thing that they were missing. Why, though, we've lost that process, we're not entirely sure. And it might just be that because if you lost your leg, you wouldn't have time to grow a new one before you became someone else's lunch, because we're warm-blooded, we're very active, and we have a high metabolic rate. You don't have months to sit around waiting to regrow yourself a new leg. You would probably have succumbed and become someone's lunch in the meantime. So maybe nature made that sacrifice in humans in order to endow us the high metabolic rate, high level of activity and a big brain we've got, whereas a lizard and a salamander and so on, it could afford to sit around under a rock with a very low metabolic rate while it regrew a new leg, and it was evolutionarily beneficial to that animal, but it wouldn't be to us.
Sure. Is it true that blood type indicates how long a tattoo will last before needing a touch-up?
Probably not, because when we do tattoos, the way this works is that the tattoo artist will use a pigment or a dye and a needle which injects this underneath the surface layers of skin into the deeper dermis of the skin. And there you get these collections of particles, which are the dye, and they are big and they sit there because they can't be carted off into the tissue. But over time, the dye molecules break apart a bit, and also cells that wander through the tissue, big cells like macrophages that eat up debris that shouldn't be there, slowly come along and chew away at some of these dyes and break them up a bit and cart them off. And that's why the edge or the margins of a tattoo begin to blur with time. That process is going to be independent of what blood type you are. It's probably more likely it's going to reflect what sorts of dyes were used. Certain dyes or pigments are going to move more or less than others, and the tattoo artist is going to know and advise you as to which ones are more likely to have a long-term lifetime. And also, we all get saggier with age. So as we age and our tissues become a bit saggier and the skin thins and the amount of connective tissue changes, that's also going to have a smearing effect on the dyes. So unfortunately, no tattoo is going to stay pristine forever.
Okay. Right. I know I'm a lot darker. I've lost a lot of my shadowings, the shadings that were there. Linda in Parkland says, morning, was Einstein's brain physically different from ours?
Oh, hi, Linda. People have looked at this, actually, when he died, and I don't know what the ethics of this was or whether Einstein actually gave permission for this to happen, but his brain was taken away and was studied, and I think there are still bits of Einstein's brain all over the place in various people's labs. They did look at it structurally because people were convinced that because he was so clever that perhaps structurally there would be differences. I believe there are some subtle differences in the structure of his brain, but not so gross as to say, well, that accounts for his genius. And in fact, if you look at anyone's brain, everyone's brain has a subtly different shape to the next person's brain because the brain is a dynamic thing. It's built as we grow and age and as we have life experiences, and that means everyone's brain has a subtly different shape and a different pattern of connections. So there may not be a gross giveaway as to why someone's clever or not, and I think that's the case with Einstein, but I think there were one or two things where people said, well, perhaps that area is a little bit more developed in him than in your average person, but I don't think there was one thing they could put their finger on and say, that is the cause of Einstein's genius, although they did look.
Particularly if it's now sort of distributed in little bits and bobs around.
Well, the way the brain works is it's not just one giant blob of chemicals that then comes up with an answer. In fact, the brain is a collection, it's an assemblage of about 100 billion nerve cells that each are making about 5,000 connections to other brain cells. So you can imagine the number of potential connections in the brain is staggering. But the brain is hived off into different areas that specialise in doing different things. There's a seeing area. So if you put your hand on the back of your head, your palm is resting roughly on the parts of the brain that are decoding what is going into your eyes. If you put your hand on the side of your head, your palm is resting over your ear and roughly adjacent to the part of the brain that's decoding where you're going to move on the opposite side of your body, what you're going to feel on the opposite side of your body. If you put your hand on your forehead, your palm is resting on the front part of your brain where last night I was at the Royal Society in London and they gave me some really hard mental arithmetic to do because they were beaming near-infrared light through my skull and measuring the blood flow in the surface of my brain. I was pretty staggered that you could do that, actually. I was amazed, in fact. But these blinking hard sums led to an enormous surge in blood flow in the front part of my brain because that's your executive centre where you're doing reasoning and you're also thinking about the humiliation of the fact that you can't do 359 take away 217 in about 20 seconds.
You've got quite a lot of pressure there. Is it true that if you eat honey from bees produced in your area, it will help reduce irritation towards pollen in your area, like sneezing, runny nose, and so on?
People say this, and I actually asked Pamela Ewan, who's an allergy specialist at Cambridge University, because we had her on The Naked Scientists a couple of years ago, and we were exploring this question of the rising tide of allergy, because we're certainly seeing record levels of people with some sort of allergy now. And she has pioneered a way of desensitising people to peanut allergy. So people who have life-threatening peanut allergies, she can get them to the stage where they're now eating peanuts. And she does that by graded exposure. They give people tiny amounts of the flour milled from peanuts, and there's enough protein in there to drive what we dub a regulatory arm of the immune system to increase its activity. And what we think is going on with life-threatening allergy is that there's a paucity or a drop in the amount of regulation. So the reactive part of the immune system is allowed to run amok. And so by gently stimulating the regulatory side of the immune system by oral challenge, you can balance those two things out and get people to tolerate to things that they previously reacted against. I therefore said to her, well, do you think that's what's going on with honey? Because bees make honey by collecting chiefly nectar, but also some pollen from plants. And so there is some veracity to say, well, perhaps if I consume enough of this honey via the oral route, I'll ape what is being done by Pamela Ewan in her peanut allergy clinic. I don't think the evidence is really, really strong in favour of doing this, but since honey tastes great, and I had honey on toast for breakfast this morning, why not give it a try? Because it's certainly not going to do you any harm, and it might make your hay fever a little bit better.
Okay, it's kind of like vaccines. Which traditional form of fossil fuel transport is kindest to the earth? Flying sounds terrible.
Well, flying probably isn't good in the sense that it does produce greenhouse gases, but it also produces them at various heights in the atmosphere and injects a lot of CO2 and other particles way up into the high atmosphere. But the actual contribution to total emissions from the airline industry is quite small as a whole. It's it's single numbers of percent. It's certainly not as bad as do you know what the biggest contributor industrially to carbon output is?
Carbon output, I'm going to say factories?
Well, it is a kind of factory, cement. In fact, making cement to build houses and motorways and so on contributes up to 40% of the CO2 that we put out around the world, because you've basically got to bake rock, and the rock you're baking is chalk and marble, like calcium carbonate, and you drive off loads of carbon dioxide to make a lime mix, which you then slake with water, and it does okay. It does draw back down carbon dioxide out of the atmosphere as the concrete goes off and sets, but the heating process itself involves the release of huge amounts of energy, which usually you get from fossil fuels. So concrete's not good, but also heating our homes is pretty awful too. Maybe 40% of a person's individual carbon footprint in a year is keeping their house warm and feeding themselves. Now, everyone's got to stay warm. Everyone's got to live in comfort and ideally and feed themselves. So we can't not do that. So we've got to think about how do we do this better. And the question was, well, what's the kindest way to do this, to travel or whatever? Well, the answer is that we're hoping to move towards more renewables in future. Electricity is clean energy as long as it comes from a clean source. So we're looking now at, can we make electricity in cleaner ways? More photovoltaics, more efficient solar, better wind energy, possibly tidal and other forms of energy like that. And that means inevitably better storage, because at the moment we can generate this stuff, but we can't store it because, of course, the sun doesn't shine at night when we need a lot of energy. Right. So people are looking at better batteries. So we have a better kind of joined up strategy where we make lots of electricity, are really good at storing lots of electricity, and then we can redistribute that electricity and then use things like electric cars to get us around. So we've basically not released carbon to get the energy in the first place.
Right. Famke wants to know, she says, at school I learned that the continental drift won't stop. We move something like 1 centimetre per year. Does the direction change, though?
Continental drift has always occurred, and it's because of plate tectonics. The surface of the Earth, the crust, which is up to hundreds of kilometres thick in some places, is floating on this squidgy layer we call the mantle. And because these plates are jockeying for position and they're all floating and moving around and redistributing on the mantle, there's always a degree of movement. The oceans have a mid-ocean ridge where they're making new seafloor, and this is pushing the seafloor out towards the margins of the oceans, where those seafloor plates are then subducted under continental plates. So we've got this whole dynamic equilibrium going on with things moving. And yes, plates move at roughly the rate your finger and toenails grow, and that's been happening for years and years and years, and in some places it's happening even faster than that. Near Taiwan, for example, there are plates moving centimetres a year. And this process is because the Earth is molten inside, and you've got this boggy mantle that allows things to flow around, and all the time the planet's got a molten interior, this is going to carry on.
Incredible. Such fascinating insight. Thank you so much, Dr. Chris Smith, the Naked Scientist, as always.
Thank you.
Have a good one.